Okay, we will see some examples of centripetal force now. I'll start with planets revolving around the sun. Planets are revolving around the sun. In this case, the force of the gravitational force of attraction, the gravitational force of attraction provides provides the centripetal force. So let us see the equations. How they work out. Centripetal force. So let's try a picture. Here we have the orbit of the sun. So it's a different color to represent the sun here. This is the sun, center, and here we have the earth, for example, and this is the radius vector from the center of the sun to the center of the earth. Just mark it as R. So small m represent the mass of the earth, and capital M represent the mass of the sun. So let's write this as sun, and let it be earth. All right, the force of attraction on the earth surrounded by the sun is marked here as Fg. So this would be the centripetal force to keep the earth moving in the circular path. So you can just write Fg provides the centripetal force, but Fcp, just put the value for Fg. Fg is equal to G times, that is universal gravitational constant, mass of the sun times mass of the earth over square of the distance between the earth and the sun. This is equals to Fcp. You may write it as m, that's the mass of the earth. This is the square of the tangential speed, and r is the radius. If you simplify this, you will get v is equals to square root of g times mass of the sun over the radius. So this is the case of, you can write a lot many equations in this case, but just for example, we just use this a very similar case. For instance, the electrons moving around the nucleus. Let's take the case. All right, put it as 2. This is the classical description of atomic model. Electrons moving around the nucleus, around the nucleus. So let's have a nucleus in here. Oh, here we have the orbit. Let's draw it again. Very similar to the earlier diagram we have here. The classical structure of an atom, and see how the equation comes out in this case. So this is the orbit of the electron, and here we have a strong nucleus. This is the nucleus nearly at the center, and here we have an electron. We just mark it as a tiny little point. Here an electron, and let's say this is the nucleus, so we can write this as charge E, the charge of an electron. Charge of a nucleus, we can write it as Ze. All right, Z times, and of course the radius we can mark it as R. And let's get the equations. As in the earlier case, the electron is attracted by the nucleus towards it. We call the force as a free. This force of attraction between this is actually the Coulomb's force of attraction, or the electrostatic force of attraction between the electron and the nucleus provides the centripetal force. So we can write here Fe is equal to Fcp. Fe will be K Z E square over R square. Again, that is equal to M times V square over R. Here, M is the mass of the electron, V is the tangential velocity, and R is the radius. And if you simplify this, as in the earlier case, we'll get V is equal to, this is the tangential velocity. You instead of G, we will get K Z E square over M, that is the mass of the electron, R is the radius, and you put everything in a square root, you will get the tangential speed. These are two typical cases where we can apply the centripetal force to get the equations of the motion of either the planets or the electrons moving around the circular path. Now let's try a little bit more complicated examples, like the case of a bicycle riding along a curved road. Let's take that example. Okay, bicycle on a curved road. So you may have already noticed that when you ride a bicycle over a curved road or curved path, you have to tilt the bicycle towards the center of curvature of the turn. So let's see how the relationships come out in this case. So I just draw a descriptive diagram here, just a functional one. Take a look here. Let's see, this is the horizontal plane representing the, here we have the road. This is the horizontal plane, it's a horizontal road. Of course, the road is curving like this. I'll show the curve. All right, this is how the road curves. Just symbolic representation. Now we have the bicycle. So this is towards the center. Now, if you want to negotiate this curve, let's have the bicycle need to be tilted towards the center. So I'm going to represent a bicycle with this line. All right. Now that is the bicycle with the center of my mark somewhere here. This is the center of mass of the bicycle. All right. Let's just mark it here. Let's draw the normal to the road here. We may probably use so like this, and what to do. Okay, let's draw the normal in here. What is it? Okay, there's a different color, so you won't get confused. This yellow gives you the normal. All right, this is the normal. Okay, I'll mark it with N. So the vertical angle, we can mark it with theta. Right. Now, the reaction force exerted by the ground on the bicycle acts along the line of the center of mass. We mark it as R. Here we go. Okay, I mark it as R in here. Now you can resolve the R into two components, one along the vertical line and the other one horizontal. So you can get here at the center of mass, this is the horizontal component of the R. So just mark it as R. And here we have the vertical component of the R. Here, vertical component of the R. Okay, here we go. And apart from the reaction, the next force acting on the bicycle is the gravitational force or the weight acting downwards. So that will be acting at the center of mass exactly down. I'm sorry, it doesn't look nice. Do it again. All right. This is the weight of the bicycle acting downward. That will be balanced by the vertical component of the centripetal force. So this angle would also be theta in this case. So you can see that this is the weight. We can write it as W, that is equal to mg. And this horizontal component provides the centripetal force. So I can write this as FCP. So we got all the equations ready now. Let us write the vertical component of the R. We can write it as R cos theta. R cos theta, that is equal to mg, balances the weight. And the horizontal component of the R, or sine theta, that would be the FCP. So you can write it as mv square over R. Now you can divide the second equation by the first one. So I mark this as 2. Right. Here we go. Here's the second equation. Here we have the first equation. So you divide the second equation. First equation, you would get m and m would cancel out. G will be on the top. V squared G no, sine theta by cos theta, that would become tan theta on the left side. That is equals to, I say, m and m get cancelled out. G comes over here, that is equal to V square over RG. Or you can write V is equal to the speed at which you need to drive the bicycle so that it won't fall off. V is equal to square root of RG tan theta. Just put it inside